A T-beam bridge is also called slab and girder. Check how to look for the geometry and the factored shear and moment of this type here in bridge engineering. We are to look for the construction parameters for a simply supported T-beam highway bridge which has 7-meter roadway width and crosses a 20-meter river. Take the wearing coat as 80 mm and crush barriers on both sides are sized at 0.6 by 1 meter. The concrete deck thickness is 8 inches and we assume the girder width as 500 mm. Use the unit weight of concrete as 24 kilonewtons per cubic meter and asphalt with 22. First is the bridge length. Compare values from two approaches and adopt the greater value. The first equation has a skew factor, and this is solved using English units. L is initially 20 meters, then use this to solve for the column height h, which is typically solved with L over 12. That is 20 meters converted into feet all over 12, which is 5.46 feet. The skew factor for straight bridges is taken as 1, so the end allowance can be computed as 8 plus 0.02 of the 20-meter length plus 0.08 of h, which was solved as 5.46, then multiply everything by the skew factor, which is 1. This results to 9.7488 inches, which is converted into SI units as 0.248 meters, rounded to 25 cm. The second equation is 0.06 L plus 100 millimeters. N is then 0.06 of 20 meters plus 100 millimeters, which makes 1,300 millimeters. Comparing the two values, we add up 1,300. So the total bridge length can be computed as the river width plus twice the end allowances. That is 20 plus twice of 1.3. This giving 22.6. So we take the bridge length as 23 meters. Now for the other parameters. Since we are using concrete, we use this table, where the thickness can be solved by the equation provided for T-beams. Note that for this equation, the thickness will be the superstructure depth, not just the deck. For simply supported concrete slab bridge, we solve T as 0.07 of L. That is 0.07 of 23,000, which results to 1,610 millimeters. This is the superstructure depth, and with the deck thickness of 200 millimeters, the girder depth is then computed as 1,610 less 200, which is 1,410 millimeters. Next is for us to assume the girder spacing as 2 meters. This is from the range for RC girders. Using S of 2, the number of girders is computed as the road width of 7 over the girder spacing assumed as 2 plus 1, giving 4.5 rounded to 5 girders. Now let's check spacing consistency. If 5 girders are used, the actual girder spacing is 7 meters over 5 less 1 girders, and that is 1.75 meters. This is different from the assumed spacing of 2 meters, so we need to iterate. Let's use the actual spacing of 1.75 meters and solve for the number of girders. That is 7 over 1.75 plus 1, which gives 5. This is the same quantity as what we got earlier, so we have finalized the number of girders as 5. We also need to verify the slab thickness that we used. With the girder spacing of 1.75, the appropriate slab thickness is from 180 to 200 mm. The assumed thickness is safe. Then we add the wearing coat. The final deck thickness is then 200 plus 80, giving 280 mm. So to summarize these parameters, T is 280 millimeters, N is 5 girders, and S is 1.75 meters. The next step is to analyze the loads. For dead loads, the tributary width is required, and for interior girders, the tributary width is 1.75, half of which is the effective width for exterior girders. dW is computed as 80 centimeters by 1.75 meters times the unit weight of asphalt as 22 kilonewtons per cubic meter. This gives 3.08 kilonewtons per meter. DC deck is the thickness of 8 inches times 1.75 with the unit weight of concrete, making 8.4 kilonewtons per meter. For the stay-in-place form, we still use 5 pounds per square foot times the remaining width of 1.75 less the girder width, which is 0.5, and DC for SIP is 0.30 kilonewtons per meter. There are also the crash barriers. Their load is computed as twice of 0.6 by 1 meter times the unit weight of concrete divided by 5, giving 5.76 kilonewtons per meter. DC for girder is the width times the depth with concrete unit weight, and that is 16.92 kilonewtons per meter. Add the miscellaneous DC of 0.2 kip per foot, or 0.03 kilonewtons per meter. Take the total dead load, having 31.41 kilonewtons per meter. For the shear and moment due to dead loads, the maximum shear is WL upon 2, and the maximum moment is WL squared over 8. With dW of 3.08 kilonewton per meter, the shear turns out as 35.42 kilonewtons, and the moment due to dW is 203.665 kilonewton meter. The DC of 31.41 kilonewton per meter, we can have shear due to DC as 361.215 kilonewtons, and the moment is 2077 kilonewtons meter. For the live loads, we again start with the design truck. And for shear, the rear axle is flushed at the support. The reaction at this support is the maximum shear, and it is computed as 1 over 23 times the quantity of 145 by 23 with 145 by 23 less 4.3 and 35 by 23 minus 8.6. The left reaction is 284.81 kilonewtons. Now let's load the design tandem. Place one of the axles flushed onto the support. Then take the reaction of that support. R1 is 1 over 23 times 110 by 23 plus another 110 by 23 less 1.2, giving 214.26 kilonewtons. Comparing these two reactions, 284.81 governs. The third is the design lane, and this is a uniformly distributed load along the span. Using 0.64 kip per foot, or 9.34 kilonewtons per meter, the reaction is solved as WL over 2. That's 9.34 times 23 over 2, or 107.41. The total shear per girder is the shear due to design truck multiplied by the impact factor plus the shear due to the design lane. V sub LL turns as 284.81 times 1.33 plus 107.41 kilonewtons, giving 486.21 kilonewtons. Now let's solve for the moment. We start by looking for the centroid of each design vehicle. For the design truck having 3 axles, we look for the centroid by using the summation of moments over the summation of forces. With training from statics, you can already deduce that the resultant of forces will be found between the two rear axles. That is where the centroid is. The summation of loads is 145 with another 145 plus 35, or 325 kilonewtons. Using the reference for bar X at the front axle, we take moments about this point and get 145 times 4.3 and another 145 times 8.6, or that is 1,870.5 kilonewton meter. We solve for bar X now, and that is 1,870 divided by 325 and get 5.75 meters from the front axle. Place the design track on the midspan, where the center line will be exactly between the centroid of the vehicle and the middle axle. This setup will keep a distance of 0.725 meters from the center to either load. Determine the reactions. By taking moments on the right abutment, we can determine the left reaction as 1 over 23 times the resultant load of 325 times 11.5 less 0.725, and that is 172.74 kilonewtons. The right reaction is 1 over 23 times 325 times 11.5 minus 0.725, which makes 152.26 kilonewtons. For the moment, we use the middle axle. The maximum moment uses the right support and the front axle, with 152.26 times 11.5 less 0.725, minus 35 times 4.3. The maximum moment is 1,490.1. Also take the moment made by the design tandem. The tandem is applied at the midspan, where the center line cuts the space between the centroid and the left axle. The distance between the center line and the wheel is 0.6. The resultant force is 220 kilonewtons, used in the determination of the reactions. The left support has a reaction equal to 1 over 23 times 220 times 11.5 minus 0.6, resulting to 104.26 kilonewtons. The right support has 1 over 23 times 220 times 11.5 plus 0.6, giving 115.74 kilonewtons. Take the moment about the right axle, where the maximum moment is the right reaction times the distance of 11.5 minus 4.3 less 0.6, giving 902.772 kilonewton meter. This moment is way less than the moment from the design track, so 1,490.1 kilonewton meter governs. The last one is the design lane, with uniformly distributed load of 9.34 kilonewton meter. The maximum moment is solved through WL squared over 8, which becomes 9.34 times 23 squared over 8, turning as 617.61 kilonewton meter. The lane moment uses the design track times the impact factor, that is 1,490.1 times 1 plus 0.33 plus 617.61, and that gives 2,599.44 kilonewton meter. The shear and moment we computed are the total lane values. What we need to do next is to take the distribution factor to know how much each girder carries. By analyzing the interior girder using 2 or more lanes loaded, the distribution factor for the moment is as shown, where S is 1.75 meters, L is 23 meters, and deck thickness is 280 mm. Kg is the longitudinal stiffness, which we still need to find. The equation for K sub G is N times I plus A times E sub G squared. N is the modular ratio of the girder and deck, and since both are made of the same material and strength, we have N as 1. The moment of inertia I uses BH cubed over 12 as the girder is a rectangle. That is 500 times the cube of 1410 over 12, which gives 1.168 times 10 raised to 11. The area is 500 by 1410, which results to 705,000 square millimeters. For E sub G, we take the distance from the center of the girder to the center of the deck. That's half of 1410 plus half of 280, which gives 845 millimeters. The stiffness parameter then is 1 times 1.168 times 10 raised to 11 plus 705,000 with the square of 845, giving 6.202 times 10 raised to 11. Now we can compute for the distribution factor using the equation. The spacing term is 1750 over 2900 raised to 0.6 or 0.739. For the span ratio term, we take 1750 over 23,000 raised to 0.2 or 0.597. Then the stiffness term is the stiffness parameter divided by 705,000 by the cube of 280, then raise the quantity by 0.1, giving 0.725. The DF is computed as 0.075 plus 0.739 times 0.597 by 0.725. Which is simplified as 0.395 or 39.5%. The final live load moment is then computed with a distribution factor. However, the moment for the wearing surface is still 203.665 and for the deck as 2077. The live load moment is 0.395 of 2599.44. Giving 1026.78 kilonewton meter. The distribution factor for shear is simpler as shown, and using S of 1750 millimeters, DF is 0.2 plus 1750 over 3600 less the square of 1750 over 10,700 or 0.659. The final shear for live load is then multiplied by this DF, but the shear for DW is 35.42 and for DC is 361.215 kilonewtons. The live load shear is reduced into 62.9% or that is 320.41 kilonewtons. With the distributed shear and moment already known, apply a AASHTO LRFD. For strength limit state, use gamma P for DW and DC, where from the gamma P table, we take 1.5 for DW and 1.25 for DC. LL is 1.75. The factored shear is computed as 1.5 of 35.42 plus 1.25 of 361.215 and 1.75 of 320.41, which is 1065.37 kilonewtons. The moment then is 1.5 of 203.665 plus 1.25 of 2077 and 1.75 of 1026.78, which makes the factored moment as 4698.61. For the service limit state, all factors are taken as 1. So the factored shear is 1 times 35.42, 361.215, and 320.41, giving 717.045 kilonewtons. For the factored moment, we use 203.665, 2077, and 986.789, giving the factored moment as 3,307.445 kilonewton meter. The fatigue limit states disregards dead loads and use the factor of 1.5 for live load. The shear is then 1.5 times 320.41, resulting to 480.615 kilonewtons. The moment is factored as 1.5 times 1026.78 or 1540.17 kilonewton meter. The last limit state is extreme event, where dead loads use gamma P, but live load uses gamma EQ. DC uses the factor of 1.25 and DW is 1.5. Gamma EQ ranges from 0 to 0.5, so to be conservative, we use 0.5. The factored shear is then 1.5 of 35.42 plus 1.25 of 361.215 and 0.5 of 320.41, which is simplified as 664.85 kilonewtons. The moment uses 1.5 of 203.665 plus 1.25 of 2077 and 0.5 of 1026.78, which brings about 3415.14 kilonewton meter. Tabulating the shears and moments, the design will be using different values according to whichever needs designing.